All right, now that we know how to graph factorable quadratics, and in particular how to find their vertex, we can tackle some of the really important types of problems that'll come up in pre-calculus and calculus. So these are optimization problems, and this one's kind of a classic. There's all sorts of variations on it, but it has some really good steps to help you get warmed up and ready for some harder versions that come up later. So we would like to fence a rectangular area as shown in this picture. So we need to go all the way around the outside, and then we also need a partition. We need a divider to go down the middle. We know that we have 2,000 feet of fencing. That's going to be a key detail. And that's kind of the only other little bit of information we have. What we would like to do is maximize the area of the enclosure. So as soon as you see that word maximize, you should be thinking vertex. So what we're hoping is that we can write a quadratic equation that represents the area, and then that we can find its vertex. So I'm going to start with A equals the area, and I think I'll just make it the total area. You could also do this as one part of the pen. If you maximize that, I think it would maximize everything for you. But I'm going to say area of whole enclosure. All right, and then you can kind of start working your way up to this. We know that area of a rectangle is length times width. So we can say that width is W and length is L. Do define these variables for me. It's really important, unless they're given to you in the problem, that you tell me what W means, what L means, what X means. And this is fine and good, but we can't maximize, we can't find a vertex of something that's not quadratic, and also of something with 3 variables. 2 variables is fine. We're equal to like y equals x squared, blah, 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 but we don't want 2 variables. So when you're doing a problem like this, you get here, and this is the point where you have to go and look for what extra information do you have that restricts you from just choosing any combination of L and W that you want. So like, why can't I say L is 100 and W is 500? And the answer to that is that the amount of fencing restricts what we can choose. So this should allow me to set up another formula. Basically, we can say that the length of the fence, this is just kind of your scratch work, so don't feel like you have to write it all out, is going to be made up of the L along the bottom, the L along the top, and then there are 3 W's. Or we can say 2L plus 3W. And then we actually know that this adds up to 2,000 feet. So if you look at what I've done, I've actually just built a 2x2 system. So if I use substitution, I should be able to make a formula for A that doesn't have both L and W. So it is important, since A is the thing that I want the formula for, I need to substitute into the A formula, which means the solving needs to happen here. It doesn't matter if you solve for L or W unless the problem tells you which one. So I think I will solve for L, and I would say that means subtract 3W, and then divide everything by 2. So that means 1,000 minus 3/2 W equals L. And now I can put these together and say that area, and I made it a function of only W, is equal to 1,000 minus 3/2 W times W. And that is my formula. And even better than that, that's in factored form. And right now what we know is how to get a vertex if you're in factored form. So what I need to do first is find the 2, it would be the W intercepts. What makes the factor 0? So one of them is W equals 0. That's just pulling that factor down. The other one is 1,000 minus 3/2 W equals 0. So I can add the 3/2 to both sides, the 3/2 W. and then I can multiply both sides by 2/3. So I get 2,000 over 3 equals W. And you can convert that to a decimal now if you would like. I'm not quite done, but let's go ahead and do that. I think it might be a little easier to reason through. So if we do that, we get that, here, I'll put it right up next to the 0. W equals 0, or W is approximately 666.67, something along those lines. And I'm giving myself a little bit of extra decimal places there. Well, not a ton, but I don't want to round too much. So what we want to do with this is say, okay, if we know that our intercepts are at 0 and roughly 667, the maximum has to happen right in the middle. So the maximum is at W equals 0 plus 666.67 divided by 2, or about 333 we'll just say 33 there. So we have the W that gives us the maximum area. This is pretty good. We're pretty close to an answer. I'm going to erase this box and box this. This is part of our answer, and this would be in feet. If we go back and reread the question, what it was actually asking for were the dimensions that maximize the area. So W is part of that answer, but L is the other part of that answer. And if you go back, you can go either to, where would we go? Like right up here, or you can go down to the one that you already solved for L and say, well, in that case, then L has to equal 1,000 minus 3/2 of our W, which is 333.33. And if we calculate that, it's actually, if we hadn't rounded earlier, we should actually end up with exactly 500 is what we should end up with there. But if you have a little bit of rounding error, I'm not too worried about that. That's fine. But that is a great answer. And again, what we've done is we've said, okay, the graph crosses at 0 and it crosses at 2,000 over 3. So the maximum has to happen at half of 2,000 over 3, which is 1,000 over 3. And that's our 333 that we got. The question could also ask you to find the maximum area, and that's really just the y-coordinate. So if that was what it was asking you, you'd take that W and you would actually plug it back into your area formula instead of plugging back into the L formula. So just reread carefully. All right, thanks for watching.